All right, chemists, so we're here at our final type of reaction. Today we're talking about double replacement reactions. It's the last of our 5 types, and it's the only reaction type that we're going to talk about that is not a redox reaction. So unlike all of the other ones, there is no transfer of electrons in this one. There's no changing of covalent bonds. This reaction is completely mediated by Coulombic forces. So here we're talking all about ionic compounds reacting with each other. Particularly, these 2 ionic compounds need to be aqueous, which allows their ions to separate from each other and actually allow them to react and change and behave independent of one another. So when one of these reactions occurs, in order for one to occur, one of 3 things has to happen. The new product either needs to be an insoluble compound, meaning something that does not dissolve in water, and therefore it forms a solid, or what we call a precipitate, and falls to the bottom. It can also form a gas, generally a small covalent compound, or it forms water. Generally that happens in what's called an acid-base neutralization, where if you take an acid and a base, those 2 ions together, they make H2O, water. So 2 important things to remember before we dive into double replacement reactions, that's going to be key to kind of understanding what's going on, is that first we need to remember again that when ionic compounds are able to dissolve in water, the cations and the anions separate from each other. This allows them to move independently and react independently of one another. Secondly, we need to remember back from when we talked about solubility, that different compounds have different levels of solubility, and that usually depends on how strongly attracted those 2 ions are. So for example, something that is soluble in water means that the attraction between the cation and anion is weak enough that the water can pull it apart. However, if something is not soluble in water, the water is not able to overcome the attraction between the cation and the anion. So here's an example of a double replacement reaction, where we're taking a solution of potassium iodide, which remember that just means it's dissolved in water, it's aqueous, and it's combined with aqueous lead 2 nitrate. So what's going to happen in this reaction, right? We want to predict the products. Now to do this, it's going to be easiest if we look at the ionic equation, just like we had done in our single replacement reactions, because we are dealing with aqueous ionic compounds. So those ions are really independent of each other. So really, it's more accurate to write this reaction as these series of 4 ions here. All right, so in my first container, my beaker, whatever that may be, I'll have these 2 ions. In my second container, I would have these 2. And then I'm mixing those 2 things together. Right, so what's going to happen when we mix them together? What are some possibilities? Let's take a look at what this looks like in a particle model form. So here on the left, I see my 2 original particle models. On the left, I have my particle model of potassium iodide. On the right, I have my lead nitrate. Once I combine those 2 things together, before they react, I'm looking at something like this particle model on the right, where now I have the sum of all those particles. I have all of the potassium ions, all the iodides, the lead ions, and the nitrates, along with the water molecules that were being used to dissolve them. So as all of those things are present in the same beaker, they can interact with each other now in new ways. Right? So some possibilities that we can see would be, for example, well, one, we could have the free-floating lead ions come next to the original nitrate ions. Now, if those 2 things come together, right, positive and negative charge, those should attract. That would be forming lead nitrate. Well, that's exactly what we had at the start of the reaction, and we already knew that water was strong enough to pull that apart. So even if those 2 things do come together again, they're not going to stay together. They're just going to redissolve, and water is going to separate them once more. Same thing if the potassium and the iodine come together. Right? Water, we already know, can dissolve that. So really, if that's the only thing that's going to happen, then no reaction here is going to occur, because we're going to have the same stuff at the end of this as we would at the beginning. So this here can't be what's happening. In the second possibility, we have a combination where we can have lead 2 cations and the potassium cations. Now, we should very quickly see that these 2 things are not going to be coming together, because those 2 things are both positive, so they should not be attracting at all. In fact, they would be repelling each other. Similar if we talked about the iodide and the nitrate. So again, we don't have to worry about this combination. That's not going to happen. Now our last possibility. Let's say instead of the lead-2 ions attracting the original nitrates, what happened if they attract the other anion in the solution? What happens if the potassium ion attracts the other anion in the solution? Well, now potentially that could give us a new compound, because now I would have lead partnering up with iodide, and I would have potassium partnering up with nitrate, which is different from what we had originally. So that could be a chemical change, but it's only going to be a chemical change if those ions actually stay together, because if water can just dissolve them again, then again, we didn't make anything new. We have the same thing at the beginning as we would at the end. So in order for this reaction to occur, one of those two products, one of those two possibilities, needs to be something that's insoluble. It needs to not dissolve in water. And if that is true, then it would precipitate, right, and fall to the bottom of the beaker or the test tube or whatever the reaction is being done in. So in this particular reaction, which we're going to see in a moment, lead iodide is actually the precipitate that forms. Lead iodide forms these yellow crystals, so you'll see them pretty apparently when we see the demonstration in a minute. So as those two ions come together, right, and they attract, they start to form this crystal lattice. They have a strong enough attraction that the water molecules are not able to disassociate them again. Right? So they're just going to sink to the bottom. Now, the potassium and the nitrate, on the other hand, those still have a fairly weak attraction. Potassium nitrate's a very soluble compound, so that one is not going to precipitate. It's just going to stay dissolved. But that's okay, because we did, in fact, make one new compound, right, this lead iodide here. So in terms of my reaction, I can now predict my products right, at the top right up here, where I have my solid lead iodide and my potassium nitrate. Using that, I can now finish out the ionic equation, because I know that at the end of this, my solid is going to be staying together. It's not going to be dissociated ions, whereas the potassium nitrate, I mean, we wrote that as a formula, but really those two are just separate ions again, and they didn't participate in the reaction at all. They didn't do anything. They didn't change. So because of that, we can bring back what we had talked about with net ionic equations, where really this is just a reaction between the iodide ions and the lead ions from two different compounds partnering up and coming together. A really easy way to tell when looking at these if no reaction is going to occur is if none of your products are solid, none of them make a precipitate, then you're going to have two aqueous products, which means that everything's a spectator ion. Everything cancels out and goes away. And if that's the case, no reaction's occurring. So let's take a look at two examples of this type of reaction. The first one we're going to see is the reaction between potassium iodide and lead nitrate, which we had just talked about and used in our particle model. And then secondly, we're going to see one between iron nitrate and sodium hydroxide. So here we're going to see the reaction between lead-2 nitrate and potassium iodide. Lead-2 nitrate's being dripped out of the pipette at the top there. As they make contact, you see the reaction occurring and the precipitate forming. That's the yellow powder there. The solid forming isn't a hard solid as we may have anticipated because the grains are so tiny. It's more of like a fine powder as they're forming. Now the reason they're not all just sinking immediately to the bottom is because they are so tiny they have to work their way through all of the water molecules and the potassium and nitrate ions. So they're kind of suspended up in the middle of the solution at the moment. Given enough time though, gravity will pull them down and they will all kind of gather and coalesce at the bottom of the test tube. So here we have our second reaction with iron 3 nitrate and sodium hydroxide. Right now we have to see the solid of each of them, so right now they're actively dissolving as those ions are moving towards each other. You can see the colors of the solution changing. And when they get into contact with each other, the ions are then able to associate with each other differently. And now we see that precipitate starting to form in the middle of them with that dark, deep brownish black line. That's the iron hydroxide's precipitate. So after seeing those two examples, right, we see that a lot of times in these types of reactions, we have a precipitate being formed. But it's possible to have this also occur by forming water, by forming a gas, depending on what ions come together. For example, on the left, we can form water using what's called, generally referred to as an acid-base reaction, where here on the left we have hydrochloric acid, which we know is hydrogen ions and chloride ions, reacting with sodium hydroxide, which is sodium ions and hydroxide. Now, if the Na and Cl find each other in the solution, that's not going to do anything for us because that just makes sodium chloride. And we know by salt water that sodium chloride is a very soluble compound, so that's not going to precipitate. However, if the hydrogen and hydroxide come together, that's going to have two H's and an O, which we know is H2O. So here we're forming water, right? Normal water, pure water, by neutralizing an acid and a base, right? Taking a piece of each of them and forming H2O. A similar thing happens over here where we can form a gas. You can generally identify gases because they are small covalent compounds. So in this case here, we're forming dihydrogen sulfide by taking the sulfide ion and the hydrogen ions from an acid and putting them together. And then lastly, here's another example of forming a solid precipitate, in this case, silver chloride. So then the big question is always, well, how do I know if a product is insoluble? How do I know if there is a precipitate? Like, I can predict what it's going to be, but how do I know if it's truly going to be a reaction? Well, to do that, we would really need to know the solubility of all these different compounds, and usually that's just not available. Right? We don't have big charts of all of the different possibilities and all the different numbers and values. So what we do use are general trends and what we refer to as solubility rules, and sometimes they're summarized in a table instead. We can use these to help us identify which compounds are most likely going to form solids, which ones are most likely going to be aqueous. So there's a reference sheet on Google Classroom. You should print it or have the link handy so you can reference it as we go through. Those of you going on to AP Chemistry next year, these are going to be one of the things that you'll be memorizing at some point in the year. So the sooner you can work towards that or understanding how we develop them, better. Now here are the solubility rules, and it looks pretty complex, but one thing that should stand out as you kind of read through them is that most of the compounds that are soluble are things that have a positive one or a negative one charge. Things that are insoluble tend to have a greater charge. Now that should make sense because we know that as the charge gets greater, the force of attraction should also increase and therefore be harder to take them apart again. But we can use these rules to kind of help us sort things out. The rules are in order of importance. So if you see two that kind of contradict each other, we can use them to use the ranking of these rules to figure out which one plays a greater role. And on the back of that reference sheet, here's a table example of the same thing, where we can use this table to figure out if compounds are aqueous or if they would precipitate and form a solid. So the big ideas for double replacement reactions. We're starting with two aqueous ionic compounds, which allows the ions to interact. The new combination of ions with a higher Coulombic force creates a product that can't be separated again, which means it's going to precipitate if it's a solid, or it'll bubble out if it's a gas, or if it's just neutralizing an acid and base, it'll make water. Some of these reactions are exothermic, some are endothermic. It depends on the reaction that's occurring. You would need to know the actual energy values of everything and the lattice energies to make that determination. And in order to help us predict the products, we're going to need to reference the solubility tables and the solubility rules. So let's take a look at a couple of examples really quick. In this first one, just so we can practice using the solubility rules, we have hydrogen ions and acetate ions because this is acetic acid. In calcium hydroxide, we have calcium ions and hydroxide ions. So again, we're looking to see what are the recombinations that could occur that would give us something new, right? A new product. Well, in this case, the only new thing that would have a cation and an anion is if calcium paired with acetate, and if hydrogen paired with hydroxide. Now right here, I'm just doing this to help me track the charges, but I need to actually make these compound formulas electrically neutral. So this for calcium acetate would be calcium and then 2 acetates to make this compound neutral. And then HOH gives me H2O. Now H2O, that's water, right? Liquid, not aqueous, because water doesn't dissolve in water. Water is just water. And then for our second other product, calcium acetate, we need to use the solubility rules in order to determine that. So using the solubility rules, one thing that we should see on there is in the rule number 3, is that compounds with the acetate ion tend to be soluble. There's a couple exceptions listed there with aluminum, silver, and mercury. Calcium's not one of them, so we can assume that this is going to dissolve. That would be an aqueous product. Now, this reaction would in fact occur because we are producing a new compound that does not redissolve again. Right? This is an acid-base neutralization example. For the second example, we have iron. I'm not sure why these parentheses are here. This should be iron with 3 plus and chloride 1 minus. Then here in potassium sulfate, we have the potassium ion and we have the sulfate ion. So we're looking for recombinations that would lead to new products. So that means we can have the iron ion and the sulfate ion. And we can have the potassium ion and the chloride ion. So making these electrically neutral means I would have Fe2SO4 3 for iron 3 sulfate, and I would have KCl for potassium chloride. Now to figure out which products would be soluble or a precipitate, I'm going to start with the KCl, because first rule always is that if you have an alkali metal, which is what potassium is, those things are always aqueous. Alkali metals always dissolve. Same thing with the ammonium compound, NH4 1+. For our second one, we're looking at iron 3 sulfate. So iron 3 sulfate, again, we can look at the solubility rules or we can use the table on the back. The table generally is faster, however, doesn't include as many things. So you kind of go back and forth using whatever works for you. From our solubility rules, we see that most sulfate compounds are in fact aqueous, and if we look on the back of the table, there is an entry for iron 3 sulfate, so we can mark this as aqueous. So, did a reaction happen here? Did we make a product that's not going to separate again? No. Both of these products are aqueous. They're both going to redissolve again. No reaction is going to occur here. In reaction number 3, we have the sodium ion, we have the nitrate ion, we have the ammonium ion, and we have the hydroxide ion. So recombinations that would occur, we can have sodium and hydroxide, we can have ammonium and nitrate. All of those have a positive 1 or negative 1 charge. So it's just going to be one of each of them to make our formulas. From my rule number 1 of my solubility rules, alkali metals, such as sodium, are always aqueous. And ammonium compounds are also always aqueous. So again, did a reaction occur? No. 2 aqueous products. Neither one is going to give us a new chemical compound that we can isolate and use. Now, one thing to note is that when we do make an aqueous product, for example, up here, it is possible to separate that from everything else. In this particular example, number 1 up here, to get this compound back to a solid, you would just need to get it to be undissolved, right, to remove the aqueous nature of it. So we can do that, for example, by heating it, boiling off the water to dry it out, leaving just that solute behind. You could do something similar to this example down here at the bottom where we have the two aqueous products. However, the problem is both of those ionic compounds would then be mixed with each other. You wouldn't have a way of isolating them just by doing that.